everyone. We'll be starting from 7:45. While we are waiting, you can feel free to ask your questions in the chat box, or you may converse among yourselves. Welcome back, enthusiastic learners. You have come a long way, and we really appreciate your consistency, enthusiasm, and thirst for new knowledge. Today, I welcome you all to the day 7 of the Machine Learning and TensorFlow Bootcamp organized by GDSE SNU in collaboration with Skepsis, the official technical committee of Sister Nivedita University. Today, we have with us Mr. Aan Patel, who is a software engineer at ShareFile Community and is the organizer of the Google Developer Group at Chapel Hill. Sir, I warmly welcome you to the session. Thank you.
Hi, everyone. First of all, thank you for welcoming me to this bootcamp. Excited to be back. Hope things are going well and guys are learning lots of stuff around machine learning. Today, we will be covering basically some items around TensorFlow and how to deploy your machine learning model that you built using TensorFlow. Let me see if I can screen share. Looks like I would probably need screen sharing access.
Sir, can you share your screen now?
Let me check. Um, okay, I think I can. Let's see if you're seeing my screen share. Is it visible?
Yes, sir, your screen is visible.
Cool, thank you. All right. So today we'll be just diving into what TensorFlow really is, and it would be all pretty much an overview of things. We would look at a lot of different code samples to get a feel of what it's like to work with TensorFlow and what it means to deploy your models with the TensorFlow platform. So let's get started. So what is the it's a huge platform which gives you tooling, which includes command line interfaces, application interfaces, which can be tied to your programming languages, and resources such as TensorFlow Hub, which lets you download tons of open source models and use them for your machine learning tasks. There are many other resources, and there's a big community behind TensorFlow. So we'll explore all of that pretty soon. But the essential piece here is that TensorFlow helps developers build and deploy ML models. So I hope by now you would know what it means to be, or what an ML model means. So it helps you develop and then also deploy your ML models. So this ranges from preparing your data to be fed to your model, to training that model, creating train and test splits, validating your model, tuning hyperparameters, and finally deploying it to some production environment. Along with that, there's also tooling in the TensorFlow ecosystem that lets you visualize and understand your models, because a lot of times these large machine learning models have tons of parameters, and it's really not humanly possible to explain how exactly a model is able to do what it is doing, right? Uh, Model explainability is a big challenge, and TensorFlow provides some resources to also aid in that. Um, Next, it gives you tooling that works on a range of platforms. So you can run your TensorFlow models from an edge device like a Raspberry Pi all the way to cloud where you might be doing some petabyte scale number crunching like companies like Google and Amazon do, right? So there's a lot of ways and use cases for which you would create ML models, and so there's different places where you would want to deploy them, right? So TensorFlow tries to serve all of those use cases. And finally, there's a large active community that's backing all of this effort to make developing ML models easier, right? That's the goal of TensorFlow. It wants to make it simple for you to build and deploy ML models. Simple as that. Um, I would pause here for questions, if there are any, um, around this broad idea of what it's like.
Hello,
I see a, yep,
am I audible?
yes.
Good afternoon. Can we say that TensorFlow is a kind of open source machine learning library?
Uh, that is a part of the TensorFlow ecosystem. So there are lots of open source libraries that can be considered a part of the entire TensorFlow ecosystem. So we will go over that in the next slides. Um, is there Are there any other questions? Okay, it will get more clear as we progress through this presentation. So, as Jamilur mentioned, one of the biggest things and something that it's kind of just known for is the APIs that it provides you for crunching collections of numbers, which it calls tensors, and building ML models around that. Right? It it's basically an open source framework or a set of contracts on how to perform number crunching, which is implemented or wrapped for lots of different high level languages. So let me explain what I mean by that. So TensorFlow gives you APIs, which are contracts basically for doing number crunching. So it will give you a list of signatures for functions that you can call, and those functions will be implemented in different languages. So you can use TensorFlow with Python, which you might have already tried before by fetching the TensorFlow library from pip, right? You might have done pip install TensorFlow, and you would have installed this API for Python, right? And then you might have used it in your Python code to train your TensorFlow model if you have worked with it before. But basically, that's what TensorFlow is. TensorFlow APIs provide, right? It has a bunch of methods and classes defined for different languages, but it's the same across these different languages, right? So the API is the same, but the implementation varies because you might want to use TensorFlow with, say, Python, or if you are a Java developer, you might want to use it on Java. and they have all of these their APIs available on all of these different languages, right? Along with that, they have wrappers that cover these other languages. So it will, under the hood, it will call the C++ APIs, for instance, but let you use them as if it's running on your on the language that you are working with, right? So it's either a port in that sense, or it's an implementation of the API contract from scratch. That's what the TensorFlow APIs and the libraries are, right? So heading back, so now you know that TensorFlow provides you APIs to crunch numbers, and we will dive into it a bit pretty soon. But that's the basic idea. So it gives you these APIs that let you crunch numbers on different environments, like if you are using a CPU or a TPU, which is a tensor processing unit, or a GPU, which is a graphics processing unit. Um, for all three processing environments, it will work across all three of them. So it won't, and there are optimizations in place under the hood that let you take advantage of the architecture of GPUs and TPUs, which is optimized for calculations. And a lot of the operations that you tend to do while training machine learning models are usually just matrix operations, right? Matrix multiplication or adding matrices and so on. So that's where TensorFlow shines, and it provides a lot of different helper APIs and classes and methods to help you quickly build up a model without having to write things from scratch. So imagine having to write a linear regression model from scratch versus doing a one-liner using TensorFlow, right? It's that's the power it gives you. And so this is the architecture of TensorFlow APIs. As I mentioned, it lets you run these high-level functions on a variety of different platforms, like on a CPU, a GPU, or a TPU, right? But at the higher level, you don't concern yourselves with these nitty-gritties. It's all taken care of by the low-level API, and need to focus on building your model using usually this one library, which is, or API, which is TF Keras. I'll wait again for questions.
Yeah, am I audible now?
Yep.
So, sir, does TensorFlow allows or provides all kind of five major APIs like web APIs, operating system APIs, library APIs, hardware APIs, cloud service APIs, all of them, or like a specific one?
Can you repeat that? I think the audio is cutting out.
I asked that the TensorFlow API supports all the five major APIs like web APIs, operating OS APIs, library APIs, hardware APIs, cloud service APIs, all of them, or like a specific one?
So these APIs are contracts, right? They are contracts that define how you can build machine learning models. So it's basically an interface that lets you define a model and then train it, or define a sequence of calculations and run them, right? So you can then, once you have built a model using these APIs, you can then deploy it to any platform, right? And execute that code to get to essentially use your model in a production application. So these APIs, an API basically means a contract, right? It tells you what you can do and what doing that thing would achieve on your system. So if it's, let me give you an analogy. You might have used Android, for instance, right? Android provides an API. So I think needs to be there needs to be a solid understanding of what an API means to then understand the concept of what is being discussed here. So an API is basically a contract, right? That lets you do things with a system. So, for example, Android provides APIs for notifications. So you can call the Android system to show a notification to the user, right? Or you can call the Android system API to show a toast to the user or show a dialog box with a message and a button, right? So that is an example of what an API is. It's basically a contract that, when used, lets you do things or interact with another system. In this case, it is your own computer, and you are trying to basically work with data, or not even your own computer, but any place where you are performing this number crunching and using the TensorFlow library. So that's basically what these libraries are about. Right? It lets you do number crunching with relative ease because it wraps a lot of the complexity under this low-level TF API, right? So you don't need to care about doing optimizations for, say, performing matrix multiplication, or using the, if you are running for every different operating system, for instance, there's a different way to interact with the kernel, right? So for each of those cases, now if it weren't for TensorFlow, you might have had to write code that would call these GPUs and TPUs with their appropriate methods to perform matrix multiplication, for instance, easily or quickly, right? It simplifies all of that for you. You just call TF matmul and it will do the matrix multiplication for you. So hope that answers your question. There's a question. Okay, so can you explain this? Okay. Jamilur, did I answer your question?
Yeah, I got it. Thank you.
All right. So yeah, that's what TensorFlow essentially provides. And you'll see as you go forward with these slides, and it'll become clearer over time. So one of the main things it gives you, these APIs also have with them an implementation of the Keras API, which is a high-level API to build and train deep learning models. So instead of having to create huge arrays and define functions that perform matrix multiplication, I will go over what neural networks are, but basically think of them as really large functions with lots of parameters that can be fine-tuned, right? And then what your task is that you want to make the output of your this really large function match with your expected results, right? So you want to do, these networks are usually intended to perform supervised learning, and so you basically have to take inputs, run them through this function. They provide you an output, um, and and then you perform gradient descent. So it's if you might remember from the previous session, we went over the concept of gradient descent and loss functions. So essentially, what you do here is this entire function has tons of parameters, and you run a batch of data through it and calculate the loss for that batch of data. Then you get a you also get a loss function based on whatever data you pass. Say you passed 10 examples of your data set into um, this function, and you got 10 outputs, and then you would get like a formula which would involve these weights and biases, which are parameters, which we'll go in much more detail in the slides to come. But it then optimizes these knobs. Each of this knob gets optimized, so you land on a function ultimately that's going to try and be as close as possible to the thing it's trying to predict, right? That's the crux of supervised learning, and that's what Keras API lets you build. So it lets you build these neural networks, and it's specialized for building deep learning models. Deep learning essentially just means building a neural network. We will go into more detail about what a neural network means, but just think about it as the more the number of layers, there's a concept of layers in here. So you basically pass an input, goes through some layers, and then you get an output or multiple outputs. And the more the number of layers, the more parameters there are to train, and the more complex your model becomes. And models which have lots of layers are called deep learning models because they are deep, right? They have lots of layers in them. So that's where the name deep learning comes from. And what Keras is, it's an API specification. Let me go over to this page. So this is the page for Keras. And it is a, as it says, a deep learning API written in Python, running on top of TensorFlow, right? So it was originally developed as a contract, and later was implemented on top of the low-level TensorFlow libraries. So going back here, so using all of these constructs, the Keras library or API was developed, right? And what it does is it calls these lower level functions and uses these lower level classes to provide yet another layer of abstraction to make it easier for you to build deep learning models. Okay, but this was, I think, the most kind of famous thing that TensorFlow is known for, right? Everyone thinks that it's just a library that you use with Python to train models. But really, the TensorFlow ecosystem is much more than that. It gives you a lot of other resources separate from this tooling and the libraries that we went over. One of them, which is really useful, is TensorFlow datasets. And these are ready to use data that you can import for use with TensorFlow, JAX, PyTorch, and many other machine learning frameworks. So it's essentially data that you can import in the form of NumPy arrays, and then you can convert them into TensorFlow arrays. In TensorFlow, they are called tensors. We will go over what a tensor is as well pretty soon. But this is an overview of TensorFlow datasets. It's basically, let me see if I can open up a page for TensorFlow datasets. Okay. All right. Let's see. Okay. Yeah. So as you can see here, it's basically a bunch of data that you can import. Let's go over to the list of datasets to see what all things they have. And on the left, you will see that they have a ton of different datasets categorized into different things. Say, for instance, you are trying to perform or trying to try out or want to try out training a model on, let's pick this one, it's malaria. So this dataset is a collection of images of blood cells that may or may not have been infected with malaria. And the task of a model that you might want to train with such data would be to classify, by looking at this image of a cell, to classify whether it is infected or not, right? And so you can import data sets like this one just by calling tfds.datasets.malaria.build. So it will let you get the data set on your Python instance wherever you are running it, be it on the cloud in Google Colab. I think you might be familiar with the concept of collabs by now. I've seen a few messages with collab links going around, so I bet you know. So yeah, that's pretty much what TensorFlow datasets gives you. Next is TensorFlow serving. So it is something that we are going to try today. It basically lets you serve your machine learning models by exposing usually RESTful APIs. And we will touch on what a RESTful API or a web API means as well. But essentially, you would want to serve your ML model, not just train it and call it a day, right? So once you build your model and train it and kind of optimize it, you want to really use it with some business application or some real life application, right? And for that, you need to deploy it to somewhere so that you can then call that model when a user needs to perform some task on your app, right? And finally, we have TensorFlow Hub, which is a repository. It's similar to GitHub if you might have used it before. It lets you import or pull in a bunch of pre-trained models. Let's go over to tfhub.dev, which is where you will see a lot of different models for different domains. So it's mainly classified into text, image, video, and audio. And you will see a lot of different options here to do things. So for instance, if you want to get a feature vector for an image, so which is basically a way to convert an image into a bunch of numbers using which you can run, say, cosine similarity or something like that to relate between, say, two different images and say if they are similar or not. So it's it's worth checking out as you start learning more about TensorFlow and start trying to build small projects with machine learning. These pre-trained models from TF Hub can be pretty useful. They also are available in different formats. So if you want to run these models on, say, a web application, you already have, for instance, a Node.js API running, you can use TensorFlow JS, which is, as you can see, it's available in this format. Models are also available in TF Lite format, which are used for which is usable on devices on the edge as well as mobile. So if you want to run your machine learning models, these pre-trained models on, say, an Android device or an iOS device, you can use TF Lite. We also have Coral, and this is a pretty niche device. So it's a tensor processing unit or TPU created by Google, which is similar in function to how GPUs do number crunching, right? It makes matrix multiplication and other matrix operations simpler and quicker, and so a lot of edge computing cases where you might have a Raspberry Pi or similar low power device, you might see a tensor processing unit like Coral attached to it, on which you would then run these models. So tensor processing units or graphics processing units are used for both model training as well as when running inference, which is when executing the model against some input. So GPUs and TPUs are used for both. Next is, well, there's nothing more. So now we can dive into tensors. All right. So this is, as you would have seen, the name of this entire ecosystem is TensorFlow, and it's named so for a reason. It Everything in TensorFlow revolves around this concept of tensors. But before we go into this, I want to pause a bit for any questions.
So, sir, in the TensorFlow, it follows a particular rule and regulation. So, in the upcoming times, nowadays, new languages and things are coming on. So, every language or every upcoming systems have to follow the rule, or it changes according to the time.
Define what you mean by rules and regulations. Can you try to explain your question in another way? Can you try framing the question in a different way? Because I think I did not get what you were trying to ask. I think I might not have gotten your question correctly, Jamilur. In TensorFlow, the contract is flexible or it's rigid for new upcoming technologies. Well, the contract is not related to new and upcoming technologies, right? So the contract is defined right? That hey, you this is what a tensor is, and you can ask TensorFlow to create a tensor for you by picking this class and calling this particular method on that class, right? So that's how this entire library and then framework on top of all that is built, right? And then if you want to change things, you will have to make a fresh iteration, because if you change it up uh, at that same version level, right, then everyone using that particular version, say you were trying to do the TensorFlow API implements the Keras library. Let's say you're trying to create a model using the Keras library, then you would do tf keras dot model, right? Um, this is, I typed it in the chat, but let's say you now want to change it with the something came up and you thought that it's more appropriate to do something like TensorFlow Keras uh, utils model. You wanted to organize it differently. Well, then it has to be a version change, right? Then it would probably be it would have to be a completely new version, say for instance TensorFlow 3, because everyone using TensorFlow 2 would have source code which would be relying on TF Keras model instead of TF Keras utils model. So if you did not version it correctly, it would break all the code that's using the previous syntax. So the syntax in that sense is rigid, but there's always planning going on at TensorFlow and in the TensorFlow community. It's open source, right? So everyone can take part in that discussion as to what the next version of this API might look like, right? Hope that answers your question. All right. Okay. So I have a collab that we can follow to kind of explore what tensors mean in the world of TensorFlow. So I posted it on the chat, and I'll also paste it in WhatsApp if people are using WhatsApp. All right. So let me shift over to that collab. And so this basically, as I was hinting at before, TensorFlow relies heavily on this concept of tensors. So you might have heard about vectors and matrices, which are a way to organize information, right? So if it's a vector, it is a one-dimensional list of things, right? That's what we call a vector. There is, and then there are matrices, which are a collection of numbers in 2 dimensions. So you organize numbers in rows and columns, and you call it a matrix. And then what happens when you go one level above that, right? Then you go into multi-dimensional space, where it's difficult to, after 3 dimensions, it becomes difficult to imagine how these numbers would be organized. But that does not stop us from organizing them in such a way. And that's how most of all calculations that happen, that you make using TensorFlow, use. They all rely on this concept of higher dimensional arrays, which are also called tensors. So you have 0-dimensional collections or arrays, which are called scalars, which are just our plain numbers. Then you have one-dimensional arrays of things, which are numbers, which is called it's called a vector. And then you have two-dimensional collections of numbers, which is a matrix. Finally, as you go into higher dimensions, we just call it a higher dimensional array or a tensor. Let's take a look at some simple examples of tensor and how you can use TensorFlow to deal with these kinds of collections of numbers, right? And let's create a few of them.
Sir, sorry to interrupt, but we have a question on the chat box.
Right?
By Rima, for pre-processing, do we need it in our ID?
Oh, looks like I might have missed it. Well, for pre-processing, we do it in our IDE. So pre-processing, what do you mean by pre-processing? There can be different meanings to pre-processing, right? It's a task. It's a thing you can do. You can do it on your computer. I can do pre-processing on my computer. I can do it on the cloud. It's just a thing you can do to prepare your data, right? Doesn't matter where it's done. What matters is how you are doing it and what you are pre-processing the data for, right? So if I'm trying to train, say, a machine learning model for that malaria data set that I just showed, I might have to pre-process and kind of look at or filter out, for instance, any images that do not conform to what this task is about. Say, by chance, there was an image of a red blood cell. Malaria is usually diagnosed by looking at white blood cells, right? So if there was an image of a red blood cell, I don't want that in my data set. I want to remove it. That's pre-processing, right? I can do it anywhere, but the end goal is to prepare data in a way I can use it to train my model. So if you are training your model locally, you can pre-process locally. Even if you're training your model locally, you might choose to pre-process it somewhere else and then download the results of that pre-processing and then use that in your model. So pre-processing or any kind of processing or building a model or anything like that can be done anywhere there's compute power, right? If it's got a CPU, it can do stuff for you. It's that simple as that. Do not box yourself into thinking that things can only run in a certain place in a certain way. It's everything's a computer, and if you really put an effort to it, you can even make use of a dummy calculator, right? Which would be very slow, but it can do things for you as well. It can run things. It would be tediously slow. It might take years or even a lifetime to get a result out of it, but you can do things anywhere, including pre-processing or training models. You can do that on your personal computer. You can do it on Google Colab, which runs a compute instance on the back end, right? And you can do it elsewhere on, say, virtual instances, like what a lot of these different cloud providers like AWS, Google Cloud, etc. provide, like AWS EC2, for instance. So I hope that gives you an overview of what it means to do pre-processing, and that there's no doubt it can be done anywhere. Okay, so moving back to this concept of tensors, unless there are any other questions, I'll wait for a couple seconds. All right, let's move on. So yeah, this is what tensors are about. They are high dimensional arrays. They can be one dimensional, zero dimensional, two dimensional, 3, 4, n dimensional. and it's basically just defining the structure of what these or how these numbers are organized and how they will be processed. So let me run this code and then take you through it. So let's first try creating a simple one-dimensional tensor. To create a standalone tensor object, you can use this construct, this constructor function. It's called just constant, and it's exported from the TensorFlow library. So you can call tf.constant followed by a list of things, and then you can specify a data type, and that will give you a tensor using the list item that you passed in. So using the list object, not item, but it's called an object in Python. So this is a list object, and I'm passing it into this constant function to get a tensor. And as a result of it, I will get back this object. And as you can see, I'm printing this, and it's going to print it out as a tensor object. So it's the class name for a tensor in TensorFlow is tf.tensor. Tf is just the alias that we are using, but that's what the class name is. It's tensor. And then it also describes the shape and the data type whenever you print it out. Any tensor, if you just use the print statement, it will convert it to string using an internal converter that's implemented on the tensor class to convert it into a string. And that gives you not just the data of your tensor, but also its shape and data type. Let's take a look at what data types there are available in TensorFlow. See if I can quickly open it up. So now you understand. We will go over all these other examples as well, but just understand that a tensor is a collection of numbers, and those numbers can be of different data types that are, let me open up a full list of them. Okay, so share this tab. Okay, so there are all of these different types available for you to use. And the reason why you need all of these different types is because some models are so large that it's very difficult to store all the parameters as large as numbers that take up a lot of space. So for instance, a lot of these data types have these numbers at the end of them and a string at the beginning. So this string tells you if it's an integer or a float, which is a value with a decimal point. And the number at the end of it tells you how many bits this type is supposed to use up. And when your models get large, it becomes difficult to deal with gradient descent and inference, right? For your entire training set if these numbers take up a lot of space. So it's computationally taxing to use larger data types. But if your model is small enough, it should still be fine. And you can use float 32 or float 64 and get away with it. But a lot of large models, like the ones you might have seen these days, such as GPT-4 or Llama or Falcon 40B, models like those that have billions of parameters, it's nearly impossible to train them at such high precision. with like say 64-bit values. And they usually use int4, which is 4-bit integers, or int8, which takes up just 1 byte of space and is less computationally taxing. Okay, moving back to tensors, this is how you can basically construct a two-dimensional tensor. So you saw what a one-dimensional tensor was. It's just a list of numbers. Now, to create a matrix, which is a two-dimensional tensor, you pass an array of arrays. To create a three-dimensional tensor, you would have to pass an array of arrays that contains arrays. So it and so on and so forth. So it's basically arrays nested inside of more arrays to give you that n-dimensional space. This is an example that will give you more idea of what it means as you proceed into higher dimensional space. So here we are using this other construct, which first we just saw tf.constant, where you have to provide the data for it to construct a tensor for you. If it's just got plain integers and you don't provide a data type, it will assume a data type of integer, int32 to be specific, as you can see here, for your tensor. If you were to provide a data type here, it will stick to that. And then you can also cast a tensor to a fresh data type, and that will basically reconstruct it under the hood to use those values that occupy more space in memory. So yeah, moving on to this tf.zeros, it's basically a utility function that returns a tensor with zeros filled in, and you provide the shape to fill those zeros in. So here you're trying to create a tensor which is 3 by 3 by 3, which will contain 27 values organized in a three-dimensional array. And in each dimension, there's 3 of each thing. So as you can see, it contains 3 matrices, basically, which takes it one dimension above the two-dimensional array. I hope this concept of tensors is making sense, because it is critical to everything in the TensorFlow world. All right, let's move ahead. Then you can initialize values based on random normal sampling. You can also initialize values as all ones. So as you can see, this is a tensor with 2 rows and 4 columns. It's initialized with all ones. Then you can initialize it with values that range randomly between -1 and 1. So that is what random normal does for you. So if you call this, it will give you a random normal tensor of shape 3 by 2. And this is used extensively for developing layers in neural networks. So if you're trying to create a neural network and you create a custom layer for it, or we haven't gotten into neural networks yet, but if you wanted to initialize the parameters for your machine learning function to something to begin with, right? And then you perform gradient descent. This is what you might use to randomly initialize those values. Imagine having to initialize an array without having this helper. You would have to run through perhaps 2 loops in Python to go over an array that you might have created and fill in these random values one by one. But because you have this helper, it becomes super quick for you to create these tensors. Next, you have linear space. This creates linearly spaced. Um, this puts in linearly spaced values into a tensor. So it will put in 5 values at equal intervals, and it will start at 0 and stop at 1. Um, and finally, there's a concept of range, which is similar to lin space, but here you can specify a starting point, a limit, and by how much, the exact value by which you want to increment it. Right? I haven't printed it out here, but this is what it looks like. So you start with 0, then you increment it by 2 until it equals or exceeds this limit value. So those are some shorthand, quick methods to initialize some tensors for TensorFlow. So now that you have tensors, this is where TensorFlow shines. It lets you do a lot of things over these tensors. It's similar to NumPy if you might have used it before, in that it lets you add and subtract tensors. It lets you multiply tensors with scalar values, which are, if you might remember, 0-dimensional values. And it will give you a result. So for instance, this is tensor addition. If I add 2 tensors, I get back a tensor with the same dimensions, but just each corresponding value gets added. If I multiply a tensor with a plain value, I get back a fresh tensor with each value multiplied with that plain scalar value. You can also do broadcasting, which means if I just try to add a scalar to a tensor, it will understand that you want to add that scalar to each and every element of that tensor and do that for you. So as you can see, we are using a matrix 1, 2, 3, 4, and then you add 5 to each. You get 6, 7, 8, and 9. And then you have reduction operations. This one is a bit tricky because it kind of goes against what you might expect a function call like this to do. In that the concept of axis is important to understand. So you have a tensor and you are trying to get the sum of values along either the columns or the rows, right? Then you can use this concept of reducing an axis. What it means is that you have 2 axes for your data if it's 2-dimensional, you have 3 if it's 3-dimensional, and so on and so forth. What it tries to do is if the shape of your data is A times A cross B cross C, then if you ask it to reduce along axis 0, it will give you 1 cross B cross C, right? So if I run this operation, it will give me a resulting tensor which gets printed out here, which would be along the columns, as you can see. So I'm running basically, let me simplify this a bit. This would still mean the same. So as you can see, you have a tensor and you're trying to run reduce sum to reduce the 0th axis, which is the first one, right? And that reduces it to this value. It basically sums up this 1 and 3 together to get you 4, sums up 2 and 4 together to get you 6. It reduces, smashes down or smooshes down the rows into 1 so that you get a single row with 2 columns. So here what you did was you had 2 by 2 reduce along axis 0, so you get 1 by 2. Now if I reduce along axis 1, I get 2 by 1, right? I get 2 rows and 1 column. And that's what we did here to get these two values. So it's really a tensor which is 2 by 1, but it still prints as a list over here. So it will in this case, I'm running mean instead of sum. So you can do reduction of uh, these tensors in different ways. Here I'm reducing along axis 1. And so it went from 2 by 2, reduce along axis 1, and then I got 2 by 1 because I reduced along this second axis, is axis 1. So axes are numbered from 0. So when I say axis 0, I mean this first one. Say axis 1 means the second one. And so you get the mean value like this. And so that's how reduction works. There's also some other examples here, like reduce max, which also performs reductions and provides max values. But in this case, it does not reduce it per axis. It goes over all elements and returns you the maximum value. So here you can see the maximum value for the matrix that we passed in this tensor is 4 among 1, 2, 3, and 4. So it returns 4. The final example here is argmax, which gives you the exact coordinates of the maximum value that you might be looking for. And it's useful for cases where, say, you have an output and you want to identify which particular element should be treated as the prediction value of your machine learning model. In those cases, you would want to get the argmax if it's like a probability array. So let's say predictions equal, and then you have classes equal cat, dog, right? And if I have 0.2, let's say I have a model that gives me a tensor back with these predictions. And in this case, the predictions are probabilities that the object that the model might be looking for, say, is a cat or a dog. And then you want to predict, whether it's a cat or a dog and print it out. And you can use argmax for it because it will give you the exact value, exact coordinate for this tensor that you can then pass into this classes list and index it to get cat or dog, right, appropriately. So that's what argmax is usually used for. You would see a lot of it in code that's written in TensorFlow. Another concept is that of reshaping tensors. So if you take a tensor and want to extend it, you get a fresh tensor back with a different shape, but with the same number of elements. So if I have this tensor, which was 2 by 2, I can reshape it into a 1 by 4 tensor, which is 1 row by 4 columns, and so on. The next concept is that of splitting and concatenation. So it's useful when you are trying to split your data set, for instance, right? If you're trying to split things into different pieces, you can use TF split. If you're trying to combine tensors together, you can use TF concat. So long as these tensors are the same dimension, it would let you concatenate them. So as you can see, it appended the second tensor to the first one and returned a fresh tensor with an updated shape. So now it has this shape of 4 by 2 because it took a 2 by 2 tensor, then concatenated another 2 by 2 tensor. So you get a concatenated tensor. Um, and to split it, well, we haven't printed the split tensors yet. It splits them back into two to give you, well, the constituent tensors as they were before. All right. Moving on to slicing and indexing. This is what you would do to access parts or elements of your tensor. So it's very similar to indexing arrays or lists in Python, in that you can provide indexes for each dimension, and it would index it by that. If it is, say, three-dimensional, then it would print yet another tensor. Otherwise, it would print, it always prints tensors, but it would print a scalar if it was an exact coordinate. If it was a range you provided, it will print a tensor with reduced dimensions for that particular range. Right. So it's pretty straightforward. You provide comma separated values for picking rows and columns, and then going into multiple dimensions, picking different points in different axes of your data, and then you can get a range of things. So here, if you want to get a column, you still have to specify this first one with a colon so that it selects all the rows, and then you can pick your column number to pick a column. And this colon is essentially using slice syntax, which is explained here. It lets you slice things. So here I'm asking it to give me everything beginning the second row and all my columns. So you can see with the matrix 1, 2, 3, and 4, I got back this. It's still, it's got two columns and a single row. So that's a basic idea of tensor manipulation, slicing, indexing, adding and subtracting tensors. This is how you cast data types. So if you had a tensor which was integer typed, you can use tf cast, provide a fresh data type. All data types are accessible under tf dot something. So you can do tf dot int 32. You can do tf dot float 16, int 16, int 8, and so on. You can cast these tensors into different formats, data formats. And it is noteworthy that you can interoperate between formats of these tensors. So NumPy, as you might have seen already, is pretty ubiquitous. A lot of data sets are stored as NumPy arrays, and even with TensorFlow datasets, so when you retrieve them, you get NumPy arrays. And if you want to convert them to tensor, it's really simple. We have a conversion utility with TensorFlow, convert _to _tensor, which will give you a tensor, basically. Okay, so that was a lot about tensors, but now you know what these tensors are in depth, so that we can start using them with machine learning models. And now we are going to actually dive into training a model, unless I have some other material. Let's see. Okay, yeah. Before we dive into it, of course, we also need to look at what Keras is, because this is the crux of training machine learning models with TensorFlow. So now you know all about tensors and what they are, and it's time to put it into action. So in order to do that, we need to use Keras. And as mentioned before, Keras is a library that lets you build neural networks. It lets you build a lot of different kinds of neural networks, but what we will be focusing on today is simple neural networks. The most simplest example of it, which is dense, fully connected, sequential feed-forward networks. It's a long name, but it's really simple when when you see it in action. And I think I have a sketch available for it. Let's see if I can pull it up. Okay. So before we dive into that sketch, just understand that neural networks, like all other machine learning models, are just functions that define a series of operations. In the world of TensorFlow, it's a series of operations over data, which is just tensors, right? Data is tensors in the world of TensorFlow. So in TensorFlow, if you're trying to build a neural network, you can think of it as just a function that defines a series of operations over a given input tensor, right? Given data, it's a function that processes those numbers and gives you a bunch of other numbers that are meaningful. A fundamental unit of a neural network is called a neuron, and it is inspired by biology. So neurons are basically things in our brains that activate given a certain signal. They don't activate all the time. They only fire or activate certain on certain occasions when some conditions are met. And this is how our brain kind of functions, right? It's instead of us in the context of computers, you writing a bunch of if then else statements, you want a machine to learn those criteria, right? Of when to activate and mark some information as 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 something. So if you want to mark some information as useful, and treat it as, hey, something has happened, you need the concept of this activation, and that's what neurons in neural networks let you do. So with that, let me move on to this sketch, which will explain the concept of neurons a bit more. So there's a lot of research that has happened in the field of neural networks, but it all started with this concept of something known as a perceptron. And a perceptron is a really simple math function which takes in a list of numbers, right? Or a vector, as they call it in maths, which can be of n dimensions. The perceptron has these weights, these parameters, these knobs that you can turn and adjust, which get multiplied with each of these values that are passed. Optionally, you have this extra weight parameter that is just multiplied with a constant like 1, which gets treated as bias. Sometimes it also gets called B. It gets marked with the letter B instead of W0, but it is essentially the same. This is what a perceptron does. It takes in a vector, does a dot product with another vector, which it knows that is the state of this perceptron. The weights that are stored are known as the state of your perceptron. And it's basically this mathematical function. It is some activation function f of this calculation. And it's really straightforward. It basically does a dot product of x with w and then adds this w0, which is here I'm calling it b, but it's really just w0. Let me open it up. I have it on my phone and I'm trying to draw things. See if I can make some corrections. All right. This is what a perceptron does. And a collection of these forms this thing called a feed-forward neural network. What it really is a large function. It's a It's a huge function with lots of W's, right? Imagine a single perceptron has all of these weights, which are parameters that you can tune, and there are lots of them, right? There are these weights for all of these, and the way a neural network works is that it operates on the result of the previous layer. So you arrange these perceptrons in layers, starting with the first one, which is called an input layer, and then you move ahead to a hidden layer, or you might not have a hidden layer. You can directly have an output layer, as this example does. And basically, what you do is you simply pass the inputs from the first layer into your next layer, and so on and so forth, and then you finally get some values which are numbers out at the end, right? And then you can train this model by figuring out its loss function and then calculating a gradient. What does that look like? So let's say it's basically a function, right? Which is, let's see if I can draw. Okay, so it's a function of right. You calculate or figure out a loss function, and then you perform gradient. Right? Loss is a function of these parameters, and then you get perform a gradient to find better parameters and change. So update. We won't get into a lot of the details of the math behind it, but the essential thing to take home is it basically tunes these values, these knobs, using this concept called gradient descent to arrive at a set of values for these weights that are optimal, that are that reduce your loss to some acceptable value. And so that's how a feed forward neural network works. It feeds the inputs, right? Just the stuff. It feeds them forward to the next layer until the end. And that's where it outputs a bunch of other numbers. And then you run a loss function over a batch of data to get to a better set of parameters. Then you do that all over again, which is in totality, when you move one step closer to the optimal parameters, it's called an epoch. And we will see that in the code example that we're going to cover next. But I'll wait for questions because this is a complicated topic. All right. So I think there aren't any questions. So we'll move forward. Before I do, I will give some examples of what an activation function looks like. So there are lots of different ways to activate your perceptron's output. And this activation function is what creates that similarity with neurons in our brains, right? So along with these weights and biases, these parameters that you tune to train your model, you have an activation function that is a part of the architecture of your model. So it doesn't change as you train the model, but it's a choice that you make upfront when training your model. Um, okay, so that is what these basic, simple, fully connected feed-forward neural networks are. So it's a bunch of these perceptron units connected to each other uh, in a feed-forward way. So every input passed to a layer gets processed, and each unit provides a fresh output, and that output is then fed into the next layer, and so on and so forth. Every time a unit receives an input, so every time a unit receives this um, input, it gets a tensor, and its output is also a tensor. So a unit is responsible for processing these tensors, and the output of each unit or perceptron here is also a tensor. All right. So moving on to what Keras now lets you do with this concept. So now you know a bit about what neural networks are. What Keras lets you do is it lets you define a neural network as a sequence of layers, and then specify how you want to get to the desired values for your weights and biases, which are those knobs that you're trying to nail correctly, right? Um, so your main task with training a neural network is to get to the right set of these parameters and reduce the loss that your model has, right? Improve the model's performance and reduce the loss. For that, you need to use an optimizer. A very common optimizer that's used uses this thing called stochastic gradient descent. Every optimizer is in some way a cousin of gradient descent, which we discussed in detail in the last meetup. But here we will go over the some source code. I think it's coming up pretty soon, which will show you what what setting an optimizer looks like, what setting a loss function looks like, so on. Keras, so it's basically two steps. You pick a type of model. In this case, we are going to pick this thing called a sequential model. The other option is to create your own custom functional model, but we won't dive into that. We will dive into this concept of sequential model, which usually serves around, I'd say, 90% of use cases when we are building these neural networks. Sequential models let you create a neural network as a sequence of layers, and once you define that sequence of layers, you can train those. You can train that defined model to get to the right parameter values. And so you will see in the source code that we first declare a model and then add layers to it, and finally call a training method that trains our model. And so here we'll go over it in the source code, which is right here. I think it's easier to explain with code rather than just with this theoretical content. Okay, so moving on to this example of training our machine learning neural network, right? We are going to use TensorFlow with Keras, and we are also going to see what this model really looks like. We are going to train a simple neural network which just has a single layer, and it will work as if it's doing just plain linear regression. So let's first install some dependencies. you don't need to concern yourselves with uh, the first one, which is just a visualizer tool that I'll be using to show what the model really looks like. But I will share this link to the Colab, which you can follow along. Um, we are going to perform linear regression, but by building a neural network. So what we are going to do is we will have this data set. It will be a very small dummy data set that has 12 features and 12 labels. The feature set and the label set are both one-dimensional tensors, right? So it's a list of numbers that map to another list of numbers, and you will see what the data looks like and how we are planning to train it. So let me run all of these import commands. And this is the crux of the whole model building exercise. So what we are trying to do is we are trying to define.
Sorry to interrupt, Aan. I think your screen is not visible right now.
Oh, okay.
I'm not sure if it's just for me or for like the others as well in the chat. But could you maybe like reshare your screen if it's possible?
Let's see. Is it?
Yeah, it's
I
visible.
might have missed out on a lot of stuff then. Okay, so sorry about that, guys. Let me see if we were on this slide, correct? Might have seen this one, and what I was covering was that. Let's see, where can we start from? So I was covering neurons, which need an activation function, right? And then we dug into that sketch. Let me share that sketch again. So I'll quickly go over this concept. There's this concept of perceptron, which takes in a vector, multiplies it with, or does a dot product with another vector, which is parameters that are stored for this perceptron itself. And there's an extra number, a scalar value called a bias that you can also optionally add or have in your perceptron's calculation logic. So you are trying to build a big function that is slightly that is able to understand or extract information in ways different from what just a simple linear equation might be able to do. So what you're trying to do is, if I have a linear function, f of x equals ax1 plus bx2, where x is a vector. So fx is a vector. If that function is ax1 plus bx2 plus something, right? There's a limit to what kind of information I can represent using this function. There's a limit to, I can try. It's always going to be a straight line in any number of dimensions. Let's say I'm training a linear regression model for n dimensional feature vector and a single dimensional label. So if I have a machine learning task where I have inputs n dimensions and outputs are labels in one dimension, and say I'm trying to create a machine learning function that will learn by tweaking its own parameters, right? There's a limit to what information I can represent by doing this. It's because it is always going to be a straight line or a hyperplane, as they call it. So as you increase the dimensions in 2 dimensions, which is just n becomes 1 here, but the graph becomes a 2D graph. So in that, you would get something like ax plus b, right? If n is 1, you would get x is a vector, with just a single dimension. So you would get ax1 plus, there should be a constant here as well. But since n is 1, I won't have any other x anything, right? I would just have x1. So it would be ax1 plus c, which would be the equation for a straight line. And so you can say that the model is able to represent the information on a straight line, right? The data collection is represented somehow using a straight line. But what happens if your data is a bit more complicated? What if your data is something like this? There are data points here, there are data points there, there's nothing here. And now if I try to draw a line or do anything like that, it's not going to fit the kind of data I'm trying to kind of predictions I'm trying to make, because the straight line just wouldn't cut it. And in those cases, you need to have these larger functions which are non-linear. So the key property to know about these machine learning models is that they let you represent non-linear relationships. So if you tweak these weights and biases for each of these units correctly, if you tweak the weights and biases for each of them correctly, you get the power that you don't with just these linear models. And that's where this shines. It lets you represent information in more ways than or learn information in more ways than a simple linear model or even a quadratic model using some quadratic equation can ever achieve, right? So that's where the power of neural networks lies. Now moving on. So as I mentioned, we'll be trying to build a neural network with Keras, which would just be a single unit this time because we are trying to see what exactly is going on under the hood. But then I'll also quickly run through an example of how larger models are trained and what they are capable of doing, because we are running out of time. So, okay. Essentially, to build a neural network using Keras API, you need to use this concept of building models using some method calls and using some helper classes that are available. If I try to get back to my presentation, this is how you create neural networks using Keras. So you define it as a sequence of layers. As you saw in the sketch, it's a sequence of different layers that perform a certain operation on a tensor that is treated as input to that layer, right? And then finally, the output of your neural network would also be a tensor. And then you run it against a loss function to optimize your parameters. So every time you calculate the loss, you will then iterate on your parameters to get to a better value for those weights and biases. That's how you train this neural network. A sequential model, of course, needs layers, and the Keras API lets you define layers, which are basically a function that take as input a tensor. That's simply what a layer does. It takes as input a tensor and gives out a fresh tensor. And the key of the concept of a layer is that you can use variables, and it's not a variable in the sense of a Python variable or a variable that gets stored in memory, but it's a concept in TensorFlow which lets you declare that some value needs to be tweaked as you calculate loss and train the model. So if you create a custom layer, you can define what are the different weights, for example, in our case of defining a perceptron layer. you can define all of those as variables, and then TensorFlow will know that, hey, this is a variable I need to tweak it at every single epoch of gradient descent, right? Every single time I try to run gradient descent, I need to update the values of these variables. Everything else, if it's not declared as a TensorFlow variable explicitly, it won't be treated as such, and it won't be trained, or that value would not get updated with every single time. Every single time you run gradient descent to update model parameters. There's also a lot of different non-trainable layers that help you transform your data. Some of them, let me share this tab to get into the API reference. So this is how you declare a sequential model. You declare it using this keyword. You use keras.sequential, then you provide a list of layers. And that's as simple as that. You now have a neural network. So we will explore what this dense means. It is a kind of layer that is pre-created for you. And if I go over to the API reference, you can see there is a page for dense layers, which will, let's see if I can. So they come under the category of core layers. There are some other layers as well, like convolution layers, pooling layers, recurrent layers, which we won't touch on during this session, but essentially they all perform some operation on a tensor that comes in and provide a tensor as output. And this is how it does that. So this page describes how exactly it performs the calculation to get the output tensor. So for every layer, the calculation might be different, but for this layer, it is done in this way. So the output of this layer is always going to be a dot product of whatever tensor is input into it with a kernel, and everything is a tensor here. So a dot product works slightly differently than you would perhaps think of doing a dot product between two vectors, because dot product of two tensors is not the same as dot product of two vectors unless they are both one-dimensional. So it's basically similar to matrix multiplication. It will perform if you have, let me see if I can pull up the sketch. Let me share that tab. Let me draw something very quick. Sharing the right screen. Okay. Yeah. So if the input tensor is A by B, and then it will assume that the kernel has to be dimensions. Let's say you have a batch size as well. So I haven't yet explained what batches are. So let's just stick with this one, I guess. Let me move here. Okay, so I have a tensor of shape A by B by C, and I'm trying to run it against a kernel, right, which is of dimensions tensor input kernel, and these are all dimensions. So I'm doing a tensor of A by B by C. I'm trying to use a kernel, and depending on whatever the dimensions of your input are, it will infer the dimensions of your kernel. In this case, what it does is it will automatically take the units as the second dimension, and the last dimension, so C, will be treated as its first. So C, and then you have units, where units are a calculation of which are resulting from the first two, which are A and B. All right. Okay. It's a bit hard to explain this in the time we have, but just understand that it takes in a tensor and gives you back another tensor, and that should be enough for what we are trying to train today. Moving back to the code example. See if I have. I think I sent the link to this code example as well. So what we are trying to do here is create a sequential model with a single dense layer, which will take all inputs, which is just going to be an input of this form, right? Input format will be of dimensions. The input tensor will be of dimensions 1, which you specify here by writing input shape. So when you add a layer, if it's the first layer, you need to specify the input shape so that it can infer how big of a kernel, which is a kernel is weight matrix. We went over the weight matrix when we were discussing perceptrons. So the kernel is just that. It's basically that weight matrix that will get tweaked or tuned as the model gets trained. And then once you define this model with a dense layer, you then compile it to have an optimizer which will decide how exactly it will perform gradient descent. Here we have an optimizer that is known to be working well with root mean squared. So that is the loss function. So we are basically trying to pick an optimizer, which is an algorithm that will perform gradient descent for you over your loss function to find the proper parameters, find the values for this weight matrix that forms the kernel. So essentially all the values in the kernel are called kernel parameters or kernel values, and it will try to get to kernel values which give you the least loss. And here is where you provide the metrics. And metrics are different from the loss function in that metrics determine the performance of your function, and they are used by you to judge how well it's performing. But the loss function is something that's used by the learning algorithm to improve the parameters and get to the place where the parameters are optimal for your model. So this is a function that will build the model with a thing that you can tweak. So if I call build model with an argument, which is learning rate, it will put that learning rate into this optimizer. So I will get back a model that will try to learn at the rate that I provided. What is learning rate? It is the rate at which gradient descent happens. We also discussed this in the previous session. basically it lets you move down to the value where the loss to the combination of parameters where the loss function has the least value. So if it's in 3 dimensions, if you remember, we looked at the parabola where 3D paraboloid, where we tried to go down to the place where the loss function was the least. So that's what the optimizer will do for you. Loss function, it just calculates the error for each prediction, and then you also can specify this metrics, which is just information for you to see if the model is working right or not. And to train your model, you call model.fit. What that does for you is it takes in a set of features, labels, to train that model, right? And you can optionally provide a batch size. What is a batch size? Well, it is the part of your entire data set. It can have 100 examples, and you're trying to train it to be good at a certain. You don't want it to be overfit, right? You don't want it to be exactly representing the data that you gave it, but you want it to get the essence of that data, so that when it gets some new example that it has never seen before, it still works and gives you an output that makes sense. That's what you use batch sizes for. But in this case, the batch size is probably, since we just have 12 data points, this is the data set that we have. It's a list of numbers that map to another list of numbers, and this is what the neural network is trying to predict, right? So we are trying to train the model, which has a single dense layer, and with certain hyperparameters like the batch size, epochs, as well as learning rate. So there are, I bet you would have in these 2 weeks come across these terms. We also covered hyperparameters before, so I won't go into detail, but it's things that are not changed when the model is training, but they are things that you can provide before you train the model, and then you can change it and train the model again to see how these different values work out and pick up the best combination for your hyperparameters. Okay, let's quickly run. I think I missed a couple of these, so it should probably give me an error. Okay. So this is where we call the function to build the model. It creates the sequential model with a single layer. And the single layer provides you, as mentioned before, it provides you an output, which is another tensor, right? That's what it trains things against. And as you can see, there's no logic in here that we are putting in to kind of actually get the output of the layer and change the parameters on that layer. Everything is taken care of by TensorFlow. So this entire weight matrix, it completely gets taken care of by the model itself, by TensorFlow. You just need to call model.fit to fit that model. Let's see what it really looks like once you train it. So I have set it to do 50 epochs, which means it will go through 50 iterations, go through multiplier. The learning rate is the multiplier or the speed at which you perform gradient descent. So if you make the learning rate too large, it's possible that it always overshoots the point where the loss function is the least. And so you never arrive at the value where the loss function is the least. But if you set it to a value that's acceptable, then you will probably get good results. And so it's a trial and error thing. You need to try different learning rates. Epochs just lets you tweak how many times I want to update my weights in the neural network. So the epochs is what decides how much you want to train this model, right? Batch size is just the size of the number of examples to take at a time to calculate the loss function. So what the loss function would look like would be L equals some number times some weight plus some number times some weight plus something, right? In this case, there is just one weight because our input tensor format is input tensor is shape 1 comma nothing, which is just a single dimensional vector, and in this case even that is just a single value. So every example that gets passed to this neural network will just have a single number. And so the dense layer, what it will have to do is multiply its heading back to this. Now you will see what it means to do this calculation here. So you're trying to calculate output, which is some activation function over this dot product of input and kernel and adding a bias. So what it converts to is this. So loss is, I'm calculating loss for one example. So loss for one particular data point is going to be something like, this is the data point's actual value. I think we can pick a data point value to give you a solid example as well. So let's say I'm trying to calculate the loss for this my underscore feature is my feature set, and I'm trying to get the predicted value of my neural net for this first feature. So what the dense layer would actually output is that it will take this number, which is currently, it's just 1, right? That's my feature value coming in from the data set. That's the feature value. And then it will multiply it with my weight, which is the kernel. And then you would add a bias at the end. And so finally you get this. Now the weight and bias would always be set to random values, right? They are set to random values to begin with. And so I will get a calculated loss value. How are we calculating loss here? Well, we defined a loss function above, which is mean squared error. If it's just one example we are dealing with, the mean doesn't apply here, because a mean only applies when you have more than one example. If I just have one data point, it will look something like this. Let's say I'm calculating loss for a batch of data of 2 data points. Then it would be something like this. This is my prediction value. And then I would subtract it with the actual value, which is for the first feature, the predicted value, the actual prediction is 5.0. So I will do this, right? And then I will square it, because this is squared error. And then I would again, and this, because I'm trying to do a mean, it would look something like this. I'm now taking the second example, which is 2.0, and then multiplying it with the same weights and biases of my perceptron, right? Of my dense layer, then subtracting it with the actual prediction, which is for 2.0, the prediction was 8.8. So I put that back here. This is what is actually happening under the hood. And then I square it. So this is square error for the second example, and this is a square error for the first example, and I sum it up and divide it with the number of examples I was trying to calculate the loss for. So here I was just trying to calculate the loss for 2 examples. I divide it with 2. So that's why I get this function. And as you can see, this loss function, if I put in some value for W1 and W0, I get the actual value of the loss function. But if I want to optimize this loss function, what I do is I treat it as a function of W1 and W0, right? This is my loss function. And what I want to do is minimize this function, right? This is for just 2 data points. Now imagine adding up all of these computed values for all of my data points. So there are 12 data points in total, and that is what this batch size is doing. So the batch size is essentially taking all of these data points, and it providing a batch size of 12 does makes it calculate a loss function that accounts for all 12 data points. Usually you would put in a subset of your data so that it picks up a random sample of these. So if I take like 4 or something for my batch size, what it will do is it will pick like the first 4, for example, or some random 4 examples from here to tweak the parameters instead of using all 12 of them at the same time. What that does sometimes is it improves the way your model understands the data, because you're presenting different facets of your data and not everything all at once. So sometimes it's helpful, not sometimes, but it's almost always every time that you need to provide a batch size smaller than the actual size of your data set. But here it's just a toy example. So we are using just a batch size of 12. But you can put a 4 here and or any number less than 12 or greater than 1, and it will batch it accordingly. So yeah, and finally you get the loss curve and you get RMSE. So the output of this function is what you get when you fit the model. So there are 2 things that we declared above. First one was build model. This function built your model and returned the TensorFlow model object. And then you can call fit on that model object and pass in your data to train it. And finally, you get the performance and everything using this history object that is returned from your model.fit call. So whenever you call model.fit, returns a history object, and it contains a list of epochs. We discussed what epochs were, and it also provides you a I think we might be able to see actually. Yeah, okay. Yeah, so this is how at every epoch you can see the loss function, which was this thing that we created. This was just for 2 samples, right? But if I had for 12, this is what it did for us. It's too lengthy to calculate by hand, but it does that in a matter of seconds, right? It took the loss down from a very high value down to almost 0. And here it's not a 0 to 100 value because it's a root mean squared error value, but you can see I think it's almost down to 0, which is always a good thing. So the final loss function value was 5, and it doesn't have any units for this because it's just a calculated value. It's not percentage values; it's just a real number, and it's trying to minimize that loss value. And the root mean squared error, it doesn't really use that for performing the training. It's something that it's outputting because you provided it as a measure that you wanted to see. So anything you provide in metrics, it will print that for you as it trains. Right? And finally, it will also print it down here once the function once the model is trained. Let's look at what the model looks like now. As you can see, it's very simple. Anytime you declare a model, it will automatically add an input layer, which is not going to be using any conversion. It will just pass in the data to the layer that you had created. And you might see that the activation function that we have used here, we haven't dug a lot into activation functions in neural networks, but the activation function is basically a function that we discussed it a bit in the perceptron example. So we discussed it a bit here, up here. This is the activation function, which runs over your computed value. So to make a small correction, the function that we defined here, there's also another function that applies to this computation, right? Which is the activation function. So it's something like this. But in this case, if you might have seen, the activation is linear. What that means is it's a function, a linear activation function is just this. It's literally, it maps the input to its output. So whatever was the result of doing this, 1.0 times W1 plus W0 is what gets returned after running the activation function. So the equation for our loss function still remains the same. And if you might have done linear regression by hand, you will see that it's the same equation that you might have seen with just plain normal linear regression without using these neural networks. So I think that should give you a course idea, a basic idea of what TensorFlow does for you, how you can train a neural network with TensorFlow, what an epoch means, what a lot of these different terms like these mean squared errors, these biases and weights, what all these mean, and what optimizer means, what a loss function means, how to configure it to create a model and then train it. So you basically create a model, then you call train function. That's it. You have a model that's ready to be deployed. And that's the next part, which I will quickly gloss over because I think we are already way over time. I would love to do a second session with some more details now that you have a basic understanding of Keras and TensorFlow, where I could go over these things in more detail. But we will use this thing called TensorFlow, which we discussed briefly in the beginning of this session, to deploy and serve a TensorFlow model. I think we might not be able to actually deploy it, but what I will show you is how exactly a model can be trained in this fashion and then deployed. So here they are trying to create a neural network. I've opened this page where it will show you a full demo of how you can train and then serve a TensorFlow model using TensorFlow serving, which is their service for serving your model in a production environment. There is a lot of other stuff as well, like TensorFlow Extended and Vertex AI pipelines and Kubeflow pipelines, which are some concepts that are extensively used in the industry to professionally manage your entire machine learning. I guess the entire machine learning department at a company would be using things like those that I just mentioned. They would be using Kubeflow pipelines or Vertex AI pipelines. I have that in a bit of information on that in my slides, but it's basically some stuff that you can use to create a structure around how exactly your model is going to be trained, where it's going to be deployed, and how exactly you are maintaining its or managing its retraining, right? Because in most enterprise companies or in a lot of applications, you would want the model to update with time. Say if you are on Amazon, you want the recommendations to update, right? Similarly, so that's why you want to then look into these things like TensorFlow extended, and there's a whole bunch of things around building pipelines that let you do that. But for now, what we are going to do is run a server that will let you make an HTTP request to it to call your model. So now it will go one step further from just running stuff in Colab to actually deploying it to somewhere. But in this example, it's actually going to be running on Colab as a kind of a local server. And you will see how you are able to make API calls to it. So I'll share this link in the chat. But this is what TensorFlow serving looks like. Where can I share my? Okay. So you have essentially this code that you are trying to deploy as a service and be able to call it via an HTTP request, right? So there's a whole bunch of code that's associated with training a model, but I'll just explain briefly what this model does. I'll not explain all of the imports that it's making, but I'll go over how it's creating that model. So if there's a lot of data preparation up here. Scrolling down, this is where it defines a sequential model, just like we did for the linear regression example. But in this case, you will see there are more layers and different kinds of layers. So here they are using a convolutional layer, which reduces the size of the input tensor to a lesser size usually, and then this layer is a layer that is not trainable. So convolutional layer is trainable, the dense layer is trainable, but the flattened layer is just an operation. If you remember about layers, there are two kinds of them. One is that which can be trained. The other is non-trainable layers. The flattened one is non-trainable. So it just takes all of the values in the incoming tensor and unfolds them into a single value. So you will see that the output shape of the tensor coming out from the first layer is 13 by 13 by 8, but the output shape coming out from the second layer is the multiplication of all three of these numbers, which is 1352, which means it combines all of those into a single vector and then passes it to the next layer. And in the next layer, the way this works is every previous layer passes each of these values. So each of these 1352 values get passed to each of the units on this next layer. There are 10 units on this dense layer. There are 1300 units here. So it will basically take these 1300 something values and run a similar operation as to what we were looking at in the code example before, which is just W1, X1 plus and so on. But the N for the dimensions in X in this case would be 1352. So there would be 1352 parameters on each unit of this layer, and optionally there could be an extra parameter each for the bias, so weights and biases, right? This layer, as you might still remember, this is not trainable, so it won't have any parameters. This layer is trainable and it will have parameters. There's a bit of some more involved calculation with convolutional layers, but you can just think of it as just another operation on tensors that give you this tensor for now. And it's useful for extracting information about parts of an image. So this model is trying to take an image which is 22 pixels by 22 pixels and predict whether it's a sandal, a shirt, or a pant. It's basically a clothing data set that you're trying to train this model against. So you train the model, you call model compile to build it, you call model.fit to train it, and finally you print out the accuracy of it, which is, it's pretty good. It's 87%, not perfect, but still fine. Here's where you do the serving. So you save the model to a file. This is the first step in serving. You save the model to a file, and then you use that file anywhere, on your computer, on the cloud, anywhere else to serve it. TensorFlow provides a interface, a CLI, a command line interface, to help you serve these models. And it is over here. So it is just performing some installation steps that are needed to get those command lines available, to make those command lines available. Once they are in place, you can then serve the model using this command. So you can call model server, pass the model directory where you saved the model. You can provide a model name as well, and provide a port on which the model will listen to requests at. And finally, you will have your model that you can call using an API request like this one. So you might have used your web browser to make API requests. I'm not familiar if you have worked with JSON APIs, REST APIs before, but basically think of it as one computer trying to call another function on some other computer and get back a result, right? That's what these APIs are used for. And what this does is it runs this model at a particular port, which keeps listening for any requests. If the Colab instance was open to the internet, you could even call it from, you can call my Colab instance from your computer and make the call against my model. But really, it's not open in that sense. There is no public IP address that you can use to call the model at the moment if it's trained on Google Colab. But if you train it on, say, an EC2 instance on AWS, if you run this command after pushing the files to an EC2 instance, right? If you run this command using the AWS CLI, you will get the model running, and you will be able to call it using the public IP address of that instance. And so that's how you serve a model in TensorFlow serving. And that's how you deploy your model to production. I think that is a lot of material to cover for today. Because we tried to take in TensorFlow, neural networks, Keras, and model deployment. So we weren't able to get through everything through like hands-on demos. I would be happy to do a second session. I think this is information overload. But yeah, let me know if there is any questions that you might have. And thank you for sticking around. I think, there's a lot of concepts to understand here. And I think this was my first time explaining these things. So I might not have done full justice to what we were trying to achieve. But yeah, if there's any questions, I would be happy to take them up here or on WhatsApp. Um, Whenever you guys go over this stuff again, I will also share the presentation in on WhatsApp. Um, but yeah, that's about it for today, I guess.
Thank you so much, sir, for the wonderful session. Everyone, please fill up the feedback form given in the chat box. As we come to the end of day 7 of the Machine Learning and TensorFlow Bootcamp, I stand before you filled with pride and excitement for all that we have accomplished together. Over the course of this event, I hope each one of you have taken something from today's session that will help you in the long run. Fret not, because it's not the end. We'll be continuing with episode 8 on the 31st of July. Till then, keep learning and keep enjoying. Thank you so much.
Right. Thanks all. Bye.
Thank you so much.